Have you ever looked up at the night sky and wondered, what are our stellar neighbors really like? Not just the stars we see twinkling overhead, but the ones closest to us in the vast ocean of space. Beyond our own sun, what's out there? What kinds of stars are near us, just past the edge of our solar system? Are they quiet, strange, dangerous, or maybe familiar in ways we didn't expect? The space around us isn't empty. It's a neighborhood filled with stars, systems, and unseen worlds. Within just 16 light-years, about 151 trillion kilometers, there are around 50 star systems. Most of them are dim red dwarfs, invisible without a telescope. A few are paired together in slow orbits. Some are so faint we didn't even know they were there until recently. And scattered among them, planets. Some small and rocky. Some too hot or too cold. And a few that sit right in the zone where water could exist. We'll visit these nearby stars one by one, starting from the sun and heading outward, step by step, deeper into space. We'll stop by Proxima Centauri, just over 4 light-years away, with its Earth-sized planet caught in a dangerous orbit. We'll pause at Alpha Centauri, a double-star system that feels oddly familiar. We'll pass rushing stars like Barnard's, quiet loners like Wolf 359, and bright giants like Sirius. Each stop is a different kind of star, a different kind of story. Some with planets, some without, some still waiting for us to understand them. It's a short journey by galactic standards, but every step takes us farther than we've ever gone. Let's begin where everything begins, with our star, the Sun. A fiery light breaks through the edge of the world. It's the Sun, the only one we've ever touched, the only one we've truly studied up close, and the only one that's given us life. This is where our journey begins. We often forget that the Sun is a star. It doesn't feel like one because it's so much brighter than the stars we see at night. But that's only because it's close. Extremely close. At least in space scale. The average distance between Earth and the Sun is about 149.6 million kilometers. To put it into perspective, if you could hop in a car and drive straight to the Sun, at a steady 100 kilometers per hour, never stopping for food, sleep, or fuel, it would take you about 170 years to get there. A commercial airliner flying at around 900 kilometers per hour would take roughly 19 years. And that's just one way. The scale is massive. And yet, in the language of astronomy, this distance is considered small, local even. Because the Sun is so close compared to everything else in space, scientists gave this particular distance a name. 1 astronomical unit, or 1 AU. It's become a kind of ruler we use to measure distances within our solar system. Mars is about 1.5 astronomical units from the Sun. Jupiter is about 5.2 astronomical units. And Pluto, it is roughly 39 astronomical units. Every planet's orbit can be measured in relation to this one fundamental stretch of space between us and our star. It's a baseline, a yardstick made from sunlight. But of course, in space, light doesn't just bring warmth. It brings time. Light from the sun travels at nearly 300,000 kilometers per second. Even at that incredible speed, it still takes over 8 minutes, specifically 8 minutes and 20 seconds, for that light to reach Earth. That means when you step outside and feel the sun on your face, you're feeling something that happened 8 minutes ago. If the sun were to suddenly die out right now, it would still appear to shine, at least for 8 more minutes, before we'd even know anything had happened. The sun is not just a ball of light in the sky, it's a complex, dynamic engine of matter and energy. And more than that, it's our reference point. Everything we know about other stars begins with understanding this one. It's close enough to study in detail, and from it, we've learned the basic vocabulary of stars, their structure, their behavior, their life cycle. The sun is our first language in the universe. At the very center of the sun is the core. You can think of it like the engine of a car, except way hotter and much, much more powerful. In this core, the sun squeezes hydrogen atoms so tightly that they fuse together and become helium. This process is called nuclear fusion, and it releases a lot of energy, enough to light up everything you see around you. Every second, the sun fuses about 600 million tons of hydrogen. About 4 million tons of that gets turned straight into heat and light, which then travels outward and eventually reaches us. Surrounding the core is the radiative zone. This part acts like a thick crowd at a concert, where energy has to slowly bounce from one person to the next. It can take thousands to millions of years for energy to pass through this zone. After that comes the convective zone. Here, it's like a pot of boiling soup. Hot plasma rises, cools down, then sinks again, over and over. These currents carry heat to the surface. The sun's visible surface is called the photosphere. It's around 5,500 degrees Celsius. That's what we see when we look at the sun. Above that is the chromosphere, and then the corona, its outer atmosphere. The corona is a mystery because it's way hotter than the surface. While the photosphere is thousands of degrees, the corona reaches into the millions. What we call sunlight is actually a tiny part of what the sun sends out. It gives off ultraviolet rays, infrared heat, radio waves, and X-rays. It also sends out solar wind, a stream of charged particles that can sometimes cause the northern lights when they hit Earth's magnetic field. Sometimes, the sun erupts with flares or coronal mass ejections, shooting huge clouds of plasma into space. These can mess with satellites and even power grids on Earth. So the sun isn't always calm. It has moods, just like anything else alive with energy. The sun is made mostly of hydrogen, about 74%, and helium, about 24%. The last 2% includes everything else: oxygen, carbon, iron, and more. That may not sound like much, but that small bit is super important. It's what helped form the planets, including Earth. It's also one of the reasons we know the sun isn't a first-generation star. It came from a cloud of gas and dust that had already been enriched by other stars that lived and died before it. In a way, the sun carries stardust in its DNA. In the classification system of stars, the sun is called a G-type main sequence star, also known as a yellow dwarf. It's the kind of star that's not too big, not too small. It sits somewhere in the middle. It's not the brightest or the hottest, but it's stable. That's important because stars that are too massive burn out quickly or explode. The Sun, by contrast, is steady and long-lasting. It's already been shining for about 4.6 billion years, and it's expected to last about 5 billion more. And it's big, really big. The Sun makes up more than 99.8% of all the mass in our entire solar system. Every planet, moon, asteroid, and comet combined is less than 0.2%. If the whole solar system were a giant scale, the Sun would tip it almost completely. Its gravity holds everything in orbit: Earth, the Moon, Jupiter, even distant Pluto. So far, only a few spacecraft have been sent to study the Sun directly, but none as ambitious as NASA's Parker Solar Probe. Launched in 2018, it's not flying straight into the Sun, but instead orbiting it again and again in a shrinking spiral. With help from Venus's gravity, each orbit brings it closer, allowing it to enter the Sun's outer atmosphere, the corona, multiple times. What makes this mission so important is what the probe is doing during those close passes. It's measuring the magnetic fields that ripple through the Sun's upper layers. It's collecting particles from the solar wind, the steady stream of charged particles constantly flowing out into space. It's also recording bursts of solar energy during flares and storms, helping scientists understand how space weather forms and spreads. Other missions have also watched the Sun, though from farther out. NASA's SOHO, the Solar and Heliospheric Observatory, has observed solar storms since 1995. The Solar Dynamics Observatory gives us stunning images of solar activity. While ESA's Solar Orbiter, launched in 2020, studies the Sun's poles and its magnetic fields. Together, these missions have turned our home star from a blinding ball of fire into a rich subject of science. We've measured its heartbeat, tracked its mood swings, and mapped its winds. And yet, it's just one of many. The Sun is special to us because we orbit it. But in the grand scheme, it's only one average yellow star in a galaxy full of possibilities. Now, it's time to leave our home star. We lift our eyes from the Sun and look outward, past the planets, past the frozen edge of our solar system, toward the vast darkness between stars where the nearest neighbor waits, Proxima Centauri. It's not a bright beacon in the sky. You can't see it with your eyes, even on the clearest night. Proxima Centauri is a red dwarf star, small and faint. If the Sun were a blazing spotlight, Proxima would be more like a dim ember glowing in the distance. And yet, it's the closest star to us, our first stop in the sea of stars. Proxima Centauri sits about 4.24 light-years away from the Sun. That may sound close, and in cosmic terms, it is. But 1 light-year is about 9.46 trillion kilometers. Multiply that by 4.24, and you get a distance of over 40 trillion kilometers. That's so far that no spacecraft we've ever built has come close. Even if you were riding on Voyager 1, the fastest object we've sent into deep space, it would still take more than 73,000 years to get there. Imagine driving your car non-stop at highway speed. You wouldn't reach Proxima Centauri in your lifetime, or your children's, or their children's. You'd need thousands of generations just to make the trip. That's how far even our nearest neighbor is. Proxima is about 1/8 the mass of the Sun, just 12% as heavy. Its diameter is around 200,000 kilometers, or roughly 1.4 times the size of Jupiter. That's tiny for a star. If you replaced our Sun with Proxima, Earth would freeze over. Its light wouldn't be enough to keep our planet warm. In fact, if you stood on Earth and looked up at a sky with Proxima as our star, the sky would look almost pitch black. It's that dim. Proxima's surface temperature is also much lower than the Sun's. While the Sun's surface is around 5,500 degrees Celsius, Proxima is only about 3,000 degrees. That cooler temperature gives it a reddish glow, which is why it's called a red dwarf. It gives off only about 0.17% of the Sun's energy. That's less than 1/5 of 1%. So it's quiet, soft, and in many ways, invisible. But don't let the small size fool you. Proxima is still a living star, and it has a personality, one that's not always calm. Proxima is known for being active. It's a flare star. That means it randomly blasts out huge flares of radiation and charged particles, sometimes many times stronger than anything the Sun puts out. These flares come from magnetic storms that snap and crack in its atmosphere, releasing bursts of energy. For any orbiting planet, these flares pose a significant threat. They can strip away atmospheres, damage surfaces, and make the environment unstable for life. And yes, Proxima does have planets. In 2016, a team of astronomers, led by Guillaume Anglada-Escudé, made a breakthrough discovery. They found a planet orbiting Proxima Centauri. The discovery of this world, named Proxima B, came from years of careful observation and data analysis. The team was part of the Pale Red Dot campaign, an international effort to look for planets around our nearest stellar neighbor. They used a method called the radial velocity technique. This method doesn't detect the planet directly. Instead, it looks at how the star moves. As a planet orbits a star, its gravity tugs on that star just a tiny bit. The star wobbles, back and forth, almost like a slow dance. These wobbles are incredibly small, but they can be measured using sensitive instruments. In this case, they used the HARPS spectrograph, mounted on the 3.6-meter telescope at the European Southern Observatory in La Silla, Chile. HARPS is like a stethoscope for stars. It listens for changes in the light from a star to tell if it's moving toward us or away from us. Over time, they noticed a regular pattern. Proxima Centauri was wobbling every 11.2 days. That wobble meant something small, but not too small, was pulling on it. Based on the size of the wobble and the mass of the star, they calculated that the planet doing the tugging was at least 1.17 times the mass of Earth. It orbits its star once every 11 days. That's because it's extremely close to Proxima, about 7.5 million kilometers away. For comparison, Mercury orbits the Sun at about 58 million kilometers. Proxima B is practically hugging its star. Because Proxima is so dim, this close distance puts the planet in what scientists call the habitable zone, the area where liquid water could exist. But could doesn't mean does. The problem is, Proxima's flares might be strong enough to destroy any atmosphere the planet has. Without an atmosphere, water can't stick around. No air means no protection from radiation, no pressure to keep water liquid, and no climate stability. Some scientists still think it's possible Proxima B might have some form of shield, like a strong magnetic field. But so far, we just don't know. We haven't seen the surface. No photos, no landers, just distant measurements. Later, another planet was found, Proxima C. This one is much farther out and much larger, possibly a mini Neptune. It's not likely to be habitable, but it's interesting. And there might be more. A third planet, Proxima D, has been hinted at. It's very small, possibly less than a quarter the mass of Earth, and very close to the star. Whether it's a real planet or just a signal glitch is still being debated. Despite being the closest star system to Earth, no spacecraft has ever come close to reaching Proxima Centauri. Our farthest traveled probe, Voyager 1, launched in 1977, is still inside our cosmic backyard, less than 1/7 of a light-year away, after nearly 50 years of travel. At that pace, it would take more than 73,000 years to reach Proxima. The gap isn't just distance, it's technology. But that hasn't stopped people from dreaming. One of the boldest concepts yet proposed is Breakthrough Starshot, a project announced in 2016 by Russian billionaire Yuri Milner, with support from physicist Stephen Hawking and Facebook founder Mark Zuckerberg. The goal is ambitious: to send a fleet of tiny interstellar probes called starships to Proxima Centauri within a human lifetime. Each probe would be no larger than a coin and weigh only a few grams. They wouldn't carry rockets. Instead, they'd be attached to ultra-thin, lightweight sails, about 4 meters wide, made of materials like graphene or mylar. The plan is to fire an array of Earth-based lasers at these sails, pushing them using light pressure. With enough energy, the probes could reach speeds of up to 20% the speed of light, about 60,000 kilometers per second. At that speed, they could reach Proxima in just over 20 years. These tiny spacecraft would carry cameras, sensors, and communication tools, all miniaturized to the extreme. Once there, they could snap images of Proxima system, like Proxima B, study its atmosphere, and send data back to Earth. It would be our first direct look at a planet in another star system. And for that first visit, Proxima makes a natural target, not just because it's close, but because it's part of something bigger. And that's what we're heading next. As we drift farther from Proxima Centauri, the darkness of space thickens again. But we don't go far. Just over 0.2 light-years away, still within the same cosmic neighborhood, 2 brighter stars come into view. They shine with a steady, familiar warmth, not too different from our own sun. These are Alpha Centauri A and Alpha Centauri B, the second closest star system to Earth, and the next stop on our journey. Together with Proxima, these 2 stars form a triple star system known as Alpha Centauri. While Proxima is the closest to Earth, Alpha Centauri A and B are the most visible. In fact, if you live in the southern hemisphere and look up on a clear night, you've probably seen them already. They appear as a single bright point of light, one of the brightest stars in the night sky. What you're actually seeing are two stars so close together that your eyes can't tell them apart. But through a telescope, they separate, two golden lights dancing around each other in slow, precise loops. Astronomers have known about Alpha Centauri for a long time. It was first catalogued in 1603 by German astronomer Johann Bayer, who gave it the name Alpha Centauri because it was the brightest star in the constellation Centaurus. For a long time, people believed it was just one star, a single point of light shining steadily in the southern sky. It was only when telescopes became powerful enough that scientists realized there was more to the story. What looked like one star to the naked eye turned out to be two bright stars orbiting each other in a slow, graceful loop. These were eventually named Alpha Centauri A and Alpha Centauri B. Then came a surprise. In the early 20th century, astronomer Robert Innes discovered a third star nearby, Proxima Centauri, a faint red dwarf hiding in plain sight. It was dim and distant from the main pair, but moving in the same direction. Over time, scientists confirmed that Proxima was gravitationally bound to Alpha Centauri A and B, forming a triple-star system. So what we once thought was a single light in the night sky was in fact three stars, a close-knit family, quietly orbiting together across millions of years. Later, in the 19th century, scientists like Thomas Henderson and Manuel John Johnson took the next step. They used a method called stellar parallax to measure how far away Alpha Centauri really was. As Earth moved around the Sun, Alpha Centauri appeared to shift slightly in position against the backdrop of more distant stars. By measuring that tiny shift and knowing the size of Earth's orbit, they were able to calculate its distance. Their results revealed something astonishing. This bright star system wasn't just another light in the sky. It was our nearest stellar neighbor, sitting just 4.37 light-years away. With the system mapped, let's slow down now and meet the stars themselves, one by one. Alpha Centauri A is the larger of the two. It's about 10% more massive than our Sun and roughly 1.5 times as bright. Its surface temperature is around 5,800 degrees Celsius, just a bit hotter than the Sun. If you replaced our Sun with Alpha Centauri A, Earth would still be in the habitable zone, and life might continue much as it is now. This star is classified as a G2-type star, just like the Sun. In other words, it's a yellow dwarf, middle-aged and stable. A star like this can live for billions of years. Alpha Centauri B is smaller and cooler. It's about 90% the mass of the Sun and shines with about half the Sun's brightness. Its surface temperature is around 5,300 degrees Celsius, which gives it a more orange color compared to Alpha Centauri A's yellow-white glow. This star is a K1-type star, known as an orange dwarf. These types of stars tend to be quieter and live even longer than stars like our Sun. The two stars orbit each other every 79.91 years. That means one full loop takes nearly 8 decades. Their orbit isn't a perfect circle. It's more of an oval, or what scientists call an ellipse. At their closest, they're about 11 times farther apart than Earth is from the Sun. At their farthest, That stretches out to 35 times the Earth-Sun distance. Even at their closest, the stars are too far apart to tug on each other's planets in any serious way. This gives each one its own space to host a planetary system. And that's where things get really interesting. For decades, astronomers searched for planets around Alpha Centauri A and B. For a long time, they found nothing certain. It was frustrating. Here we have stars so close, so sun-like, and yet no planets we could confirm. But in 2012, scientists from the European Southern Observatory announced they had detected a planet around Alpha Centauri B. They called it Alpha Centauri AB. It was believed to be a rocky world, perhaps Earth-sized, orbiting its star every 3.2 days, way too close for life. Unfortunately, the signal was weak. Later reviews suggested it might have been a false positive caused by noise in the data. For now, that planet remains unconfirmed. Years later, in 2021, astronomers, using a telescope called the Very Large Telescope in Chile, discovered something else. A possible planet orbiting Alpha Centauri A. The planet wasn't seen directly, but hinted at through a method called infrared imaging, which looks for the faint warmth of a planet rather than the light it reflects. This object was detected about the same distance from Alpha Centauri A as Neptune is from our Sun. If confirmed, it would be a giant planet, maybe something like Saturn or Jupiter, orbiting quietly on the edge of its system. More discoveries might still be ahead. The Alpha Centauri system is now a top target for exoplanet hunters, especially those looking for Earth-like worlds. NASA's upcoming missions and telescopes, including the James Webb Space Telescope and others in development, may help us finally get a clearer look. The system has also inspired dreams of interstellar missions. Before breakthrough starshot focused on Proxima, Alpha Centauri A and B were often mentioned as potential destinations. You've probably heard the name before in films or books. Alpha Centauri is a favorite setting for alien civilizations, future space colonies, or interstellar missions gone wrong. It appears in Avatar, Mass Effect, Sid Meier's Alpha Centauri, and dozens of other works. That's no accident. It's the closest place that feels like it could be something like home. And if we ever did manage to stand on a planet in the Alpha Centauri system, the view of the sky would be unlike anything from Earth. From a planet orbiting Alpha Centauri A, you'd see Alpha Centauri B shining brightly nearby, far brighter than our moon. If the system has moons or rings, they'd be bathed in a golden-orange light. Proxima, though distant, would appear as a faint red dot in the background, still part of the family, just farther away. Alpha Centauri A and B show us what it looks like when stars share a space and still manage to shine on their own. Two suns circling slowly in the dark, whispering possibilities. If there are planets there, especially in the right zone, then it's not hard to wonder what kind of climates, skies, or maybe even life might exist. For now, we listen, we watch, we imagine. But our journey doesn't stop here. There's another star just a little farther out. It's not bright, it's not flashy. In fact, it's one of the dimmest stars visible through telescopes. But it's famous, studied for over a century, and it moves faster than any other star in the night sky. Our next destination is Barnard's star, the silent sprinter of the stellar neighborhood. At first glance, there's not much to see. You can't spot it with your eyes from Earth, even on the clearest night. It doesn't glow warmly like Alpha Centauri A. It's dim, quiet, almost invisible. But don't let that fool you. This little red star is on the move, racing through the galaxy faster than any other star near us. And despite its small size and quiet nature, Barnard's star has captured the imagination of astronomers for more than a century. Barnard's star lies about 5.96 light-years away from Earth, which is around 56.4 trillion kilometers. That's just a bit farther out than Alpha Centauri, and it makes this red dwarf the fourth closest individual star to the Sun, right after the three members of the Alpha Centauri system. Not far, but far enough that visiting it would still take tens of thousands of years using today's spacecraft. The star is named after American astronomer E. Barnard, who discovered its unusually fast movement in 1916. At the time, it wasn't the distance that shocked scientists, it was the speed. Barnard noticed that the star seemed to be shifting across the sky much more quickly than other stars. By measuring its position over the years, he realized it had what's called a high proper motion, the fastest ever recorded at the time. Barnard's star moves about 10.3 arc-seconds per year across the sky. That might not sound like much, but in star terms, it's like watching a snail sprint. Over a human lifetime, its position in the sky noticeably changes, which is incredibly rare. Now let's zoom in closer to this fast traveler. Barnard's star is a red dwarf, a type of star much smaller and cooler than our Sun. Specifically, it's a spectral type M4 star. That means it's deep in the red category, with a surface temperature of only about 3,100 degrees Celsius. Our Sun, for comparison, burns at roughly 5,500 degrees. Because it's so cool, Barnard's star doesn't shine very brightly. Its total brightness is just 0.04%, that of the Sun. If the Sun were a blazing spotlight, Barnard's star would be a dim red nightlight tucked away in a corner. You'd need a good telescope to see it at all. Despite being dim, it's old, really old. Estimates suggest Barnard's star is between 7 to 12 billion years old. That's almost twice the age of our Sun. Think about that. This small, quiet star has been burning steadily for most of the life of our galaxy. It's already lived through generations of stars being born and dying, including some that went supernova, and it still has trillions of years to go. Red dwarfs like Barnard's star burn fuel slowly. Unlike massive stars that blaze through their energy and die young, red dwarfs are frugal. They sip their fuel. They live for what seems like forever. In terms of size, Barnard's star is only about 14% the mass of our Sun and roughly 20% its diameter. If you could line them up side by side, the Sun would tower over Barnard's star like a beach ball next to a marble. It's small, but stable, and it hasn't shown much of the wild, violent flaring that some red dwarfs are known for. That makes it a more peaceful target when scientists think about possible planets or even future exploration. And yes, Barnard's star has kept astronomers busy with the question, does it have planets? For decades, scientists searched. In the 1960s, Dutch astronomer Peter van der Kamp claimed he had found a planet orbiting Barnard's star, based on changes in the star's movement. But later reviews showed that the wobble he saw was likely caused by issues with his telescope, not by a planet. It was a major disappointment at the time, and for years, Barnard's star was thought to be lonely. But the search never stopped. And in 2018, a team of astronomers made a breakthrough. Using precise radial velocity data, tracking the tiny movements of the star over many years, they detected signs of a planet. The discovery came from the Carmini's and Harp's spectrographs, based in Spain and Chile. Both instruments are like the heartbeat monitors of astronomy. They look for tiny shifts in starlight that reveal if a star is being tugged by an orbiting planet. What they found was compelling. A planet roughly 3.2 times the mass of Earth, orbiting Barnard's star every 233 days. It was named Barnard's Star B. That orbit puts the planet at a distance of about 60 million kilometers from its star, somewhere between the orbits of Mercury and Venus if it were around our Sun. Now, don't get too excited just yet. While the planet is close enough to be considered potentially interesting, it likely lies just outside the so-called habitable zone, the region where liquid water could exist. Because Barnard's star is so dim, that zone is much closer than it is for the Sun. And with the planet being so far out, it's probably very cold. Estimates suggest surface temperatures around minus 170 degrees Celsius. That's colder than Pluto. Still, its discovery is a huge deal. It's one of the nearest known exoplanets to Earth, and even if it's frozen on the outside, some scientists wonder if there could be subsurface oceans or maybe some kind of geothermal activity. We don't know yet, but Barnard's Star B is now one of the top candidates for future telescope observations and even theoretical missions. As for sending spacecraft there, we're not even close. No mission has ever been launched with Barnard's star as its destination. At our current technology level, it would still take tens of thousands of years to get there. But that doesn't stop us from planning. Projects like Breakthrough Starshot, which we mentioned earlier, could one day be aimed at Barnard's star or its planet. If we could build chips that sail on beams of light, this quiet, ancient star might one day receive a visitor from Earth. Before we leave, there's one more interesting note. Because Barnard's star is moving so quickly in our direction, it's actually getting closer. In about 10,000 years, it will be at its nearest point to Earth, just 3.8 light-years away, closer than Proxima is today. It won't stay there, of course. It will keep on racing through the galaxy, always drifting, always going. But for now, it's close enough for us to study, imagine, and dream. And with that, we drift onward. The next light in the darkness is harder to see than Barnard's star. It's one of the faintest stars in our cosmic neighborhood, a red dwarf like Barnard, but with almost no activity. You wouldn't notice it unless you were looking for it, but it's there, quiet, stable, and practically invisible. Next, we reach at Wolf 359. If you turned off the lights, stepped outside on a clear night, and looked straight up, you wouldn't see it. You could stare for hours, let your eyes adjust, scan every inch of the sky. And still, you'd miss it That's how dim our next destination is. At just under 8 light-years away, Wolf 359 is one of our nearest stellar neighbors, yet it's completely invisible to the unaided human eye. You could be looking right at it and not know. It's a ghost among stars, a cosmic whisper, but it's real. And now, here we are, approaching one of the faintest stars in our entire celestial backyard. The moment we arrive, the quiet is overwhelming. Wolf 359 doesn't roar like the sun, doesn't flare up like Proxima. It just hums in infrared silence, like a dying coal in a frozen cave. It's a red dwarf, yes, like Proxima, like Barnard's, but even by red dwarf standards, it's on the extreme end of the scale. Its mass is just 9% that of the Sun. Its radius, about 16%. That makes it barely bigger than Jupiter, though much denser. The surface temperature is 2,800 degrees Celsius, cool by stellar standards. It emits less than a fraction of a percent, under 1/10,000th of the Sun's light. If our star were a lighthouse, Wolf 359 would be a match in a storm. It was discovered in the early 20th century by German astronomer Max Wolf, one of the first astronomers to truly embrace astrophotography. He catalogued it in 1919, giving it the designation Wolf 359. That number, 359, doesn't refer to its position or order of discovery, but to its entry in Wolf's personal catalogue of high proper motion stars. Despite being nearby, it remained mostly unknown outside professional astronomy circles for decades. And perhaps that's part of its charm. It's always been here, close by, hiding in plain sight. From Earth, Wolf 359 sits in the constellation Leo. It moves across the sky at a decent clip. Its proper motion is one of the higher ones known, but because it's so dim, only precise instruments can track it. It doesn't call attention to itself. No dramatic outbursts, no unusual colors, just a quiet, solitary existence. A star like this could live for trillions of years, silently fusing hydrogen in its core, never reaching the dramatic end phases that larger stars face. No red giant phase, no supernova. It will just slowly cool and dim until one day, far in the future, it becomes a black dwarf, an object we've never seen, because the universe isn't old enough yet for one to exist. There's something oddly comforting about that kind of longevity. In a galaxy of chaos, where stars explode, planets collide, and black holes twist the fabric of space, Wolf 359 simply endures. It's not flashy, but it's stable, reliable, a dim ember that's still burning quietly while everything else rushes by. There are no known planets here, not yet. Astronomers have searched, of course, scanning the star for wobbles or dips in light that might hint at an orbiting companion. So far, nothing has turned up. That doesn't mean planets don't exist here, only that if they do, they're small or distant or hidden in ways we can't yet detect. Red dwarfs are tricky targets. Their small size and faint glow make precise measurements hard. But in time, as telescopes improve, Wolf 359 might give up more of its secrets. And while it might be quiet scientifically, Wolf 359 has managed to capture the imagination of many in pop culture, especially in the world of science fiction. Perhaps the most famous reference comes from the Star Trek universe, where the Battle of Wolf 359 became one of the most pivotal events in the series' lore. In that story, a fleet of Federation ships faces off against a deadly Borg cube near this very star and loses catastrophically. The choice of this star wasn't random. It was picked precisely because it was close, yet obscure, mysterious. It was the perfect place to stage something dramatic. So, even in fiction, Wolf 359 plays the role of the quiet, hidden threat. Back in reality, no such battles rage here. Just hydrogen fusing quietly, gravity holding everything together, and space stretching endlessly in every direction. You could spend a lifetime orbiting this star and never see much change. A perfect place to hide, to think, to observe. If humanity ever sends probes this far, or even crewed missions one day, it might not be because Wolf 359 has something dramatic to offer. It might just be the next logical step in expanding our reach. A stop along the way, a node in the larger map of local stars. There's one more thing that makes Wolf 359 fascinating, and it's not something you see, it's what it teaches. Stars like this dominate our galaxy. Nearly 75% of all stars in the Milky Way are red dwarfs, and many of them are even fainter than this one. As we slowly pull away, leaving Wolf 359 behind, its faint light slipping into the backdrop of stars, it's hard not to feel a bit of awe. Not from what we've seen, but from what we haven't. Its very invisibility makes you wonder how many other stars we pass by every day without noticing. How many entire systems are drifting in the darkness just beyond our reach. But the sky is not all quiet. Just ahead, piercing the black like a cosmic spotlight, is something unmistakable. Something that doesn't hide. It is brilliant, steady, and unmissable. It's not just a star. It's the brightest star in our night sky. We are now approaching Sirius, the dog star. Look up from almost anywhere on Earth, any night, any season. And if the sky is clear and you're in the right hemisphere, you'll see it. The brightest star in the night sky. Gleaming, piercing, almost too bright to be real. That's Sirius, the next stop in our journey through the stars. At first glance, it looks like a single, brilliant point of light, dominating the constellation Canis Major, the Greater Dog. But Sirius isn't one star, it's two. A binary system, one alive and blazing, the other long dead and compacted into a ghost of what it used to be. This is where we meet extremes, the bright and the dead sharing the same patch of space. Sirius A, the one your eyes see from Earth, is about twice the mass of the Sun and about 25 times more luminous. It shines a brilliant bluish white with a surface temperature close to 9,940 degrees Celsius hotter and younger than our own star. It's only 240 million years old, a baby by stellar standards, still in the prime of its hydrogen-burning youth. If the Sun is a middle-aged engine pacing itself, Sirius A is a high-performance race car tearing through the track. But it won't last nearly as long. Its life will be measured in hundreds of millions of years, not billions. That's the trade-off for burning so bright. A short, flashy existence followed by a dramatic end. Now imagine standing somewhere in that system, perhaps on an orbiting planet. None are known here yet, but imagine, and looking up. Sirius A would blaze in the sky so brilliantly that it would cast shadows like a full moon does on Earth. The blue-white light would wash across the landscape, painting everything in a cold glow. But not far away, if your eyes were sensitive enough, or your instruments precise, you'd catch sight of its strange companion, Sirius B. Sirius B is one of the most famous white dwarfs in existence. A white dwarf is what's left after a star, much like the Sun, or even bigger, runs out of fuel, sheds its outer layers, and collapses. But Sirius B wasn't always small. It used to be more massive than Sirius A, possibly 5 solar masses. That means it lived fast and died young. After exhausting its nuclear fuel, it swelled into a red giant, and then ejected its outer layers, leaving behind a core of carbon and oxygen no bigger than Earth, but as massive as the Sun. Now, Sirius B is a dense, smoldering ember, extremely hot, about 25,000 degrees Celsius on the surface, but slowly cooling over time. It no longer produces energy through fusion. Instead, it radiates residual heat, a fading echo of its former glory. It's small, dim, and utterly invisible to the naked eye from Earth. But it's there, orbiting Sirius A in an elliptical path every 50 years, caught in a gravitational dance that's lasted millions of years. Its existence was first predicted in the mid-1800s by the American astronomer Alvin Clark, who noticed that Sirius A wobbled slightly in its motion. An invisible companion had to be tugging on it. Using the largest refracting telescope of his time, Clark spotted Sirius B in 1862. It was the first white dwarf ever observed. The discovery was more than a technical achievement. It opened an entire new chapter in astrophysics. Here was proof that stars don't simply burn out and disappear. They evolve, die, and leave remnants. That idea changed everything we thought we knew about stellar life cycles. What's truly wild about white dwarfs like Sirius B is their density. You're looking at something with the mass of the Sun crammed into a sphere about the size of Earth. A single cubic centimeter, about the size of a sugar cube, would weigh over a ton. If you could scoop up a teaspoon of its material, it would outweigh a full-grown elephant. The only thing preventing it from collapsing further is quantum pressure, a weird property of matter at atomic scales that kicks in when gravity gets too intense. Sirius B is a laboratory in space for physics at the edge. But let's not forget where we are. This isn't just a science exhibit. Sirius, for humans, has always been more than just a star system. It has myth, meaning, and history baked into our culture. Ancient Egyptians noticed its annual rising just before the flooding of the Nile and built parts of their calendar around it. To them, Sirius, called Sopdet, was a symbol of fertility and rebirth. The Greeks named it Sirios, which means scorching or glowing, due to its brightness. And even today, the term dog days of summer comes from the period in July and August when Sirius rises with the sun in the northern hemisphere, a time once thought to bring fever and catastrophe due to the double heat. Even more fascinating is how many cultures independently assigned it great significance. Aboriginal Australians considered it part of a celestial hunter. Polynesians used it for navigation. The Dogon people of Mali famously incorporated it into their cosmology, with controversial claims about their ancient knowledge of Sirius B long before telescopes existed. Whether myth or coincidence, Sirius has always held our attention. Modern science, too, hasn't lost interest. The Hubble Space Telescope has captured images of Sirius B, separating it from its bright partner with advanced optics. Ground-based observatories track the binary dance of the pair, and future space missions will likely study the system more closely, especially as exoplanet detection methods become refined enough to pierce the glare of Sirius A. Finding planets in such a bright system would be a major achievement. There's also a practical angle to Sirius's brilliance. Because it's so bright and close, it's used as a reference point in astronomical observations. Instruments are calibrated against it. Telescopes use it to fine-tune their optics. If our cosmic neighborhood had street lamps, Sirius would be one of the biggest and brightest bulbs. As we begin to move away from this remarkable binary pair, it's hard not to look back. The light of Sirius will still be visible for centuries, still shimmering through our planet's history books, still watched and worshipped and measured. But the farther we travel, the more distant it feels, not just in space, but in tone. We're leaving behind the iconic, the easy to see. Ahead lies another kind of star. Not famous, not blazing, but much closer to what makes up the bulk of the galaxy. We're heading now to Ross 128. Discovered in 1926 by American astronomer Frank Elmore Ross, Ross 128 sits about 11 light-years from Earth. That's roughly 104 trillion kilometers. If you traveled at the speed of the fastest spacecraft ever launched by humans, Voyager 1, it would take you over 200,000 years to get there. And yet, astronomically speaking, it's just down the block. Ross 128 is small, really small, just 17% the mass of the Sun. Its diameter is about 20% of the Sun's. If the Sun were a beach ball, Ross 128 would be a golf ball. Its surface temperature is around 3,000 degrees Celsius, less than half as hot as the Sun, and its brightness is only about 0.036% of the Sun's. In fact, if you replace the Sun with Ross 128, Earth would be frozen solid unless it was brought much, much closer. That's the thing with red dwarfs. Small and cool, but potentially long-lived and steady. Exactly what you want if you're hoping for planets with life. Now here's where it gets interesting. In 2017, scientists confirmed the presence of a planet, Ross 128b. It's roughly 1.8 times the mass of Earth. That's close enough to call it Earth-sized in the cosmic scheme of things. But what made headlines wasn't just its size, it was the orbit. Ross 128b orbits in what could be the habitable zone, where temperatures might allow liquid water to exist on the surface. Let's pause there. A calm star, an Earth-sized planet, sitting in the potential habitable zone. Suddenly, this quiet red dwarf starts to sound like one of the most promising places for life beyond Earth. Ross 128b completes an orbit every 9.9 days. Yes, its year is about a week and a half long, but because the star is so dim that short orbit places the planet at just the right distance to receive similar energy levels to what Earth gets from the Sun. Not too hot, not too cold, just maybe right. Ross 128 isn't just any red dwarf star. It's unusually well behaved, unlike Proxima Centauri, which lashes out with flares powerful enough to strip atmospheres and sterilize surfaces. Ross 128 is practically polite. That means its planet, if it has an atmosphere, might actually be able to hold on to it. This is very important, because atmospheres mean pressure, and pressure means liquid water. There's more. In 2017, astronomers at the Arecibo Observatory detected a mysterious signal coming from Ross 128. It was brief, it was strange, and for a moment headlines buzzed with speculation. Was it an alien radio signal or intelligent life? But as it turns out, the signal was probably from a geostationary satellite orbiting Earth. Just interference. Nothing to see here. But for a moment, Ross 128 was on the front page of Science News. Still, even without alien broadcasts, the system remains one of the most intriguing in our neighborhood. In fact, of all the potentially habitable exoplanets discovered near Earth, Ross 128b is among the best candidates. Not because it's the closest, not because it's Earth 2.0, but because it sits in a sweet spot. A stable star, a solid planet, and just enough data to keep us dreaming. Ross 128 reminds us that not all stars make a show of themselves. Some just keep burning, slowly, quietly, reliably. And in the long game of life and habitability, that might be the most important trait of all. Before we move on, it's worth appreciating just how lucky we are to be at a time in human history when we can know this much about stars we can't even see with the naked eye. Ross 128 looks like nothing special in a telescope, a faint red whisper on the edge of darkness. But thanks to high-precision radial velocity measurements, infrared observations, and decades of persistent data gathering, we now know its planet exists. We know its distance, its orbit, even a bit about its potential climate. We've come far. Now, we keep going. Because as quiet and promising as Ross 128 is, it's not alone. Out here in this stretch of space, within about 16 light-years, we find a whole community of stars. A natural neighborhood. A collection of systems, some quiet, some wild, some lonely, some paired, that form our local star cluster. Red dwarfs dominate the landscape, tiny points of slow-burning light in an ocean of cold. Let's take a deep breath. After drifting quietly past Ross 128 and its hopeful little planet, the space between stars begins to feel less like lonely darkness and more like the edge of a community. We've been treating each star like a separate island in the void, but now the landscape shifts. We are no longer visiting one isolated point after another. We're entering a cluster, a collective, a kind of natural district of space. This is our local star neighborhood, everything within roughly 16 light-years from the Sun. And for the first time, Instead of focusing on just one or two stars, we're going to glance around and see the whole street we live on. In this neighborhood, you'll find around 50 star systems containing roughly 65 individual stars and brown dwarfs. That might not sound like a lot until you realize just how quiet the rest of the galaxy is at this scale. The Milky Way may have hundreds of billions of stars, but even in what we think of as a dense patch like this one, it's still mostly empty. This is like finding a few scattered houses on a continent of wilderness. But these scattered stars, faint as they are, have stories of their own. Most of the stars here are red dwarfs, tiny, cool, dim stars that can burn for hundreds of billions or even trillions of years. In fact, red dwarfs are the most common type of star in the galaxy, but none of them are visible from Earth without a telescope. They're that faint. Out of all these 65 stars, only a handful can be seen with the naked eye, and even those tend to be less impressive than Sirius or Alpha Centauri. But just because they're quiet doesn't mean they're boring. Take Lalande 21,185, for instance. It's about 8.3 light-years away in the constellation Ursa Major. It's one of the brightest red dwarfs in the sky, not bright enough to see without aid, but still one of the stronger ones. And it's known for being one of the nearest stars with suspected planets. Astronomers believe it may host at least 2 super-Earths, though we haven't pinned down much more than that. Still, if we ever build interstellar telescopes or launch robotic probes, this would be a system worth pointing toward. Then there's 61 Cygni, a binary star system about 11.4 light-years away. It's made of 2 K-type orange dwarfs, smaller and dimmer than the Sun, but not quite as faint as red dwarfs. What makes 61 Cygni special is its motion. It was the first star, other than the Sun, to have its distance measured via parallax. That happened in 1838, and it was a huge breakthrough for astronomy. Its rapid motion across the sky, called proper motion, earned it the nickname the Flying Star. No confirmed planets yet, but its quiet, stable pair could host them. Epsilon Eridani is another local standout. Just 10.5 light-years away, it's a K-type star as well, orange, cooler than the Sun, and has one confirmed planet orbiting it. Maybe more. That planet is a gas giant, similar to Jupiter, located far from the star. What's fun about Epsilon Eridani is that it's often included in science fiction. It's the host star of the planet Vulcan in some Star Trek lore. It's also relatively young, which means any planetary system around it might still be settling down. And yet, it already has a wide dust belt, like our Kuiper belt, hinting at a full and active planetary system. Another name that pops up is Gliese 1061. Located about 12 light-years away, it's yet another red dwarf, and one that only recently entered the exoplanet conversation. 3 planets are believed to orbit it, one of which, Gliese 1061d, sits in the star's habitable zone. But remember, habitable zone only means it could have the right temperature for liquid water. It doesn't tell us anything about atmosphere, surface conditions, or actual habitability. Still, it puts the system on the map. And that's kind of the theme here. You look around, and it seems like every third star has a planet candidate. Many of them don't get much press because they're faint, they're quiet, and their planets haven't been studied in detail yet. But give it time. Over the next few decades, new observatories like the James Webb Space Telescope, the European Extremely Large Telescope, and future missions like LUVOIR or HABEX might give us atmospheric data, direct imaging, or even the first hints of biological signatures. Now, it's important to understand just how clustered this little bubble is. If you could somehow look at our region of space from above, say from 100 light-years away, and zoom in to the 16 light-year radius around the Sun, you'd see something that almost looks like a lumpy ball of stars. No spiral arms, no nebulae, just individual pinpricks of fusion-powered matter scattered in three-dimensional space. It's quiet, still, and kind of beautiful. If interstellar travel ever becomes possible, even just robotic, this would be humanity's playground for the first few centuries. We might build relay stations, settlements, scouting probes, scientific outposts. Each star a kind of port in the dark, connected by long, slow beams of data and occasional vehicles. That's what makes the local star neighborhood feel so intimate. And just think, this is only a tiny slice of the galaxy, a single dandelion seed's worth of stars in a storm of hundreds of billions. Still, for now, it's ours. Our street, our cluster, our beginning. And now, we approach our final destination on this leg of the journey. We're about to visit a system that sits just on the edge of what we might call near, a place that rounds out our tour and gives us one more reason to keep looking out. At over 20 light-years away, we arrive at a destination that once stirred headlines and sparked imaginations like few others. Gliese 581. Gliese 581 sits in the constellation Libra. It's a red dwarf, cooler and dimmer than the Sun by a large margin, emitting only about 1% of the Sun's light. You can't see it with the naked eye, but in 2007, Gliese 581 became one of the most talked about stars in the night sky. Because around it, clinging to this quiet reddish glow, were planets. Not just gas giants or scorched rocks, but something different. Something that, for a time, seemed almost Earth-like. Let's start with the star itself. Like most red dwarfs, Gliese 581 is small, only about a third the mass of the Sun, and just over a third its radius. Its surface temperature is chilly, 3,200 degrees Celsius. It's old, stable, and fairly quiet, which is what astronomers love to see when searching for potentially habitable planets. A star like this can live for tens of billions of years, providing a long window of opportunity for planets to evolve, cool, stabilize, and maybe, just maybe, foster life. Now, the planets. At least 4 have been confirmed. Possibly more, depending on how the data is interpreted. But the real story here revolves around one particularly controversial world. Gliese 581G. Back in 2010, a team of astronomers announced that they had found it. An Earth-sized planet, orbiting smack in the middle of the habitable zone of its star. It was named Gliese 581G. and for a moment, it was hailed as the most Earth-like planet ever found. It was dubbed Zarmina's World by one of its discoverers. Artists' renderings imagined oceans, clouds, and rocky terrain under a red sky. It felt close, real, maybe even reachable one day. But the celebration didn't last. Follow-up studies cast doubt on the planet's very existence. Some astronomers believed the signal that revealed Gliese 581G was actually just a statistical fluke, or the result of stellar activity being misread as planetary motion. For years, the debate went back and forth. Is it there or not? Today, most of the astronomical community leans towards skepticism. Gliese 581G is likely not real, or at least not detectable with our current tools. And yet, the system still holds other planets that are very real and still quite interesting. Gliese 581c, for instance, is about 5.5 times the mass of Earth and orbits closer to the star than Mercury does to the Sun. It's probably too hot to be habitable, but it was once considered a strong candidate. In fact, the system as a whole has become a textbook case in exoplanet detection and scientific caution. It showed how hard it is to confirm Earth-sized planets, how easy it is to overstate a discovery, but also how thrilling the process can be. Gliese 581 helped change the public imagination around space. It made people believe, even briefly, that we might be on the verge of finding a second Earth. We're still decades, maybe centuries, away from getting answers. We need better instruments. We need patience. But the beauty of Gliese 581 is that it reminded us what's possible. Even if none of its planets turn out to be habitable, the system itself pushed the boundaries of detection. It showed how fragile the signal of a small rocky planet can be, and how far we'll go to try to find it. Another layer worth mentioning, Gliese 581 was one of the first stars to receive a purposeful broadcast from Earth. In 2008, a message called A Message from Earth was sent, using the RT-70 radio telescope in Ukraine. It contained 501 messages from people around the world, aimed directly at Gliese 581c. The signal will arrive in the year 2029. If someone's out there listening, they'll hear us soon. That's both thrilling and eerie, because this is one of the few stars we've ever intentionally reached out to in that way. And so Gliese 581 stands at the edge, not just the edge of our local space, but the edge of our hope, our caution, and our curiosity. It marks a turning point, where our journey through familiar space starts to fade into the unknown. The signals grow weaker, the travel times grow longer, the dream of visiting becomes more distant. Yet even at 20 light-years, what astronomers still call nearby, Gliese 581 holds onto our imagination. It reminds us that searching for life isn't about certainty, it's about possibility. It's about building the instruments, running the numbers, dealing with disappointment, and still coming back the next day to try again. From here, our map of local stars begins to thin out. The next ones are further away, harder to study, and often less well known. But we'll always remember the journey from Proxima to Gliese, our quiet, dim local stars that stretch across space like forgotten embers. They are the ones closest to us, the ones we'll likely reach first, and the ones that, in the cold silence of interstellar space, still whisper the possibility that we are not alone. The journey we've just taken feels immense. We've drifted more than 20 light-years from the Sun, visiting stars that range from glowing giants to barely visible red dwarfs, from the violent and volatile to the quiet and hopeful. But here's the striking part. Despite all we've seen, all we've imagined, all we've marveled at, we've barely scratched the surface. The stars we've visited so far all lie within a region astronomers call the local neighborhood. That sounds cozy, doesn't it? Like we're talking about a cluster of houses in a familiar town. And in a way, it is. All these stars, Proxima Centauri, Sirius, Ross 128, they sit within just 20 light-years of the Sun. That's a bubble only 40 light-years wide in diameter. Now picture this. The Milky Way galaxy is around 100,000 light-years across. If our journey were a walk through a city, we haven't even left our front yard. Our galaxy isn't just big, it's staggering. There are more than 100 billion stars scattered across its spiral arms. Some are gathered in tight clusters, others float alone in vast stretches of empty space. And as we float here, at the outer edge of what we call near, the view stretches beyond measure. Our galaxy is waiting. One day, maybe far in the future, we'll leave this neighborhood for good. We'll build ships that travel faster, probe deeper, endure longer. We'll visit stars that today are just names on a chart. We'll decode the atmospheres of distant exoplanets. We'll listen more carefully for signals, and perhaps we'll send more messages of our own. Maybe we'll even find another blue world under another sun. But every long journey begins with the first few steps. A tour of the stars closest to us. They are few, but they are important. They anchor us, they point the way forward. So now, as we zoom out from this little bubble of space and look again at the Milky Way, its spiral arms, its glowing core, its countless stars, we can start to place ourselves in context. We are small, but we are not insignificant. We are explorers. And the stars are not just dots of light. They are destinations. The neighborhood is just the beginning.